So in section 4.6, we're going to work with fitting a line to data. Now this section is much more real world than some of the others. The others are very much part of sort of a basic education, whereas this is more the way linear algebra gets used in more commercial enterprises to actually make decisions and to analyze data. So what we're going to want to do is we're going to learn how to make a scatter plot and also how to write equations that model data. So we're going to need to know for your vocabulary what's a scatter plot, what is correlation, and what is a line of fit or a line of best fit. So when we talk about a scatter plot, in a real life situation, let's say I was going to plot monthly sales for a company, a scatter plot, the points aren't all going to sit on the same line. They're going to look something like this, or this, or this. So when you plot the points, maybe this is January, February, March, April, May, June, July, August, September, right, etc. When you plot the points, they're either going to fall into patterns or they're not. So you can see that this has a pattern, and as we move from left to right, there is a trend that the values are increasing. Okay, so this has a positive correlation. Here also there's a trend. As we go from left to right, there's a trend. So as we move forward, it is decreasing. This has a negative correlation. Now over here, the points just seem kind of all over the place. It isn't following into a specific pattern like the other two did, and so these are said to have relatively no correlation. Now if you study statistics, there's correlation analysis, and there are other things you can do to establish, is there correlation between two things? But for now, we're really just sort of going to look at it and make our best decision. So when we look at these three sets of data, you can see that as I move from left to right, generally speaking, this is increasing. This is a positive correlation. And over here, everything's just kind of all over the place. There doesn't seem to be anything. So I'm going to say there is no correlation. Whereas with these, you can see as I go from left to right, there's pretty clearly a trend downward. So this is a negative correlation. Okay, and this would be important because if we spotted a trend where we felt there was correlation, then we might want to proceed and do a line of best fit. If there's no correlation, you wouldn't do that. Okay, so let's take a look at making a scatter plot, and this is basically just me working with my data. Now, when you start making a scatter plot, you kind of want to look at your data. You want to put together the best sort of grid you can. I notice that all of my values are positive, so I'm working just in the first quadrant to make life easy. And we're looking at fish length and fish speed. Length in centimeters and speed. So as I start labeling length and speed. Okay, so when we start looking at, well, what's my length going to be? It's going to be like from 19 to 37, so it's pretty narrow there, but it's not, there's nothing in the lower end of all this, so I'm probably going to go by tens, or maybe by 5. So maybe if I go 10, 20, 30, 40, I've already gone more than I need to, so I'm going to spread that out a little more just to help have a little data. So 1, 2, 3, 4. Well, actually, maybe if I do it by 5, then I'm going by 2s. That's probably easier. 1, 2, 3, 4, 5. So that's 10. 1, 2, 3, 4, 5 is 20. 1, 2, 3, 4, 5 is 30. And 1, 2, 3, 4, 5, that's 40. Okay, so what I'm doing is I'm trying to split this up. Now, if my if my items are related to each other, like this was length and this was length, this was another measurement of size or something like that, I might want to keep the units of measure the same on the same scale, but in this case they really are relatively unrelated. Okay, and you can see that now we're talking about, I got to go all the way up to 150. I'm going to start at 40. Let's see how many spaces I've got. I'm just going to put an S for speed. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, right, that's 10 down from the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so actually coming up from the bottom, that would be 10. And this would be 20. Okay, so if I went by tens, I could say this was 200, and this is 100. And so then that's 20, 40, 60. Oops, did I make a mistake? 20, 40, 60. 80, I need to go up a little bit more. Let me make sure I'm doing this right. 20, 40, 60, 80, 100. 20, 40, 60, 80, 200. Okay, so now I've got my scale, and let's go ahead and now we can sort of plot our points. So 37.8, that's really close to 40, right? So this is 32, 34, 36, 38. Really close to 38, and we want 40, 10. Right, this is 20, and that's 48, 148. So there's 100, 20, 40, really close to 150. So this point is right about here. Right, and if I wanted to keep track, I could call that A and say, oh, this is point A, and then this could be B, C, D, E, if I wanted to label them. So this red Gernard is just about 20, right, 19.2, so right about here, and 47. So there's 20, let's see, 19.2, so right about in here. So there's 20, 40, 47 would be right about there, almost to 50. And that's point B. My black bass is a little over 20, and it's about 88. So that's 80. This is about 90. So it's just a little over 20 and a little under 90. That's point C. And then Gernard is 26.2. So 246, right about this line. And 131, so that's 2031, so right about here. D, and then 26.8 and 98, so that's really close to 126, 246, 27 would be right about there, and just a little under 100. Right about there, and that's E. Okay, so you can kind of feel like, well, maybe there's a correlation. You can see that it isn't super, right? You can see that even though these two are kind of about the same, right? That was 26.2 and 26.8. They're very close to the same, and their speeds are very different. They're still more than the smaller fish, and they're still less than the bigger fish. Okay, so you can see that there tends to be a positive correlation here. Okay, if we want to look at the idea of a line of best fit, if I went back to this data, you could see that even though my data isn't exactly right, if I sort of generically put a line sort of through the middle of my data, I could say, well, maybe that's pretty close. Or maybe I would say, well, maybe I want to come down closer to there or come up to there. And the point is, this is a line of best fit. It involves judgment, right? Who determines best? I determine best. I decide what do I think is the line that best models the data. So there isn't one answer that is absolutely correct in this. Okay, so what we're going to do is we're going to look at what is it like to go ahead and do this. You make a scatter plot, decide if it looks like a linear model, draw a line that is the best fit, and you want to try to have about as many points above the line as below it. So if you notice when I drew my line in, I had 2 above and 3 below, and you notice I'm a little closer to the 3 below because there are more of them. Okay, so I was shifted a little toward the other lines. Right? Write an equation using 2 points on the line. So what we want to try to do then is we want to pick 2 points off the line. They're not necessarily the actual data pairs, but we want to pick 2 points that are on the line. So we're going to go ahead and make a scatter plot with this data, and I'm going to go a little faster than I did the last time. Okay, so again, you notice all positive numbers. I'm working in quadrant 1, so I'm just going to make quadrant 1. We're working with years, and that's since, let's say years since 1990. Right, so back here, this is 1990, and this would be 2, 4, 6, 8, 10. That goes up to the year 2000. That's as far as we go. And then let's say 10, 20, 30, 40, 50, 60. So that's 60. This one is 50, 40, 30, 20, and 10. So when we were at 2, we'd be at 22, right about there. And at 3, we would be at 24. 4, we're at 27. 5, we're at 27 again. 6, we're at 34. That's really close to 35. 7, we're at 40. Right there. 8, we're at 42. 9, we're at 45. And 2000, we're at 51. Okay, so when you take a look at this, I might want to go ahead and I can clearly see this is very, very linear. Right? And if we take a look at trying to draw a line of best fit through this, maybe something like that looks good. Right? Maybe I can push it up a little. So that looks pretty good to me. And what I've done is I've actually picked 2 points that are part of my data set. So I've got this one. I'm going to use 2051. And actually, right, I didn't use the number 2000. I used years since 1990. That's a convention for graphing that we would normally do. 51. And then I also have picked this point here, right? And that's 1996, so that's 634. Okay, so I've picked these 2 points that are on my line that I feel best model the data. Okay, so now our task is to write an equation that models the number of active woodpecker clusters in the DeSoto National Forest in Mississippi. That's what this data is. So I have 2 points. The first thing I can do is I can figure out the slope. M is 51 minus 34 over 10 minus 6. So 51, that's going to be over 4, and 51 minus 34 is 17. 17 fourths. This is going to get a little messy. I might just call that 4, but I don't want to mess with my data too much. Okay, so if I use now point slope and I do y minus 34 is equal to 17/4 times x minus 6. Right, so y minus 34 is equal to 17/6x. That actually, I'm sorry, 17/4 x, my mistake. 17/4 x minus 6 times 17 over 4. Well, the 4's has a factor of 2 and the 6 has a factor of 2, so it'll be 3 times 17 over 2. Well, yeah, 3 times 17 over 2, so that's 51/2. And then if I want to add 34 to either side, that's 68/2. So if y is equal to 17/4 x minus 51/2, but plus 68/2. Right? And the difference between 68 and 15 is again 17. So my final, pardon me for having to skip over, is 17/4 x plus 17/2. Okay, that is my equation. So as I move on here to work with this, there's my equation. If I want to describe the domain and the range of the function, well, for my domain, I'm working in years from 1992 to the year 2000. So I would call that 1992 to 2000. Right? And for my range, my values went between 22 and 51. Right? Y actually, the best way for me to write this would be as a compound inequality. So x is greater than or equal to 1992 and less than or equal to 2000. And I'll do the same with y. Let me take a look at those numbers again. 22 and 51 are my boundaries. So y is greater than or equal to 22, but less than or equal to 51. That's my range. At what rate did the active woodpecker clusters change during the period? Well, that would be my slope. About 17/4 per year. That's how they changed. Okay, and that's working with a line of best fit. This is really commonly used in business because when we collect data about certain situations and we're trying to make sense of it, the data almost never will sit beautifully on an algebraic model, and we have to go ahead and make compromises to come out with the best fit that we can.